Good morning, everyone, and welcome to our webinar on the topic of containerization on Google Cloud. My name is Chirag Thapar, and I'm associated with Sela as a lead for cloud sales. Today, we are going to deliver one-hour session while showcasing that how you can leverage Google Container Services by using Docker, Kubernetes, and Google Container Engine. Before we kick off the session, I want to introduce you all with Sela Technology Solutions. Sela Technology Solutions India Private Limited is an Indian entity of Sela Group, which is a 3-decade young IT MNC and headquartered in Israel. Besides India and Israel, we have an existence in US, Canada, and Singapore as well. Sela Group is a technology company for past 3 decades, serving over 800 clients across the globe with around-the-clock model in various industry verticals for software development, technology consulting, cloud computing, technology training, offshoring and outsourcing, as well as product development. Sela's relationship with cloud started almost 10 years back with Microsoft Azure. Sela was the first company worldwide to train on Microsoft Azure. More recently, Sela is also providing cloud consulting on GCP as well as on AWS. Since the session is going to be focused on Google Cloud Platform, I can't get myself away without speaking about Google's cloud infrastructure, tell a bit about Google's cloud business expansions in recent times. Google has 10 regions and 30 zones up and running today with their latest announcements of Singapore and Sydney regions. All these data centers around the globe are catering Google customers worldwide, and there are 7 more regions to come by the end of December 2017, including the one in Mumbai. Google has 100 edge points around the globe to serve its customers for faster content delivery and data streaming requirements, along with a well-provisioned global network with 100,000 miles of fiber optic cable. Google Cloud Platform has a giant and robust infrastructure which enables you to avoid noisy neighbor problems, which means irresponsive systems and slow performance during peak hours and so on. Google's customer infrastructure will be mission critical as Google's own services, and the biggest revenue generators as Google.com search, YouTube, Gmail, and G-apps run on same infrastructure. In a nutshell, all GCP customers will have an access to the same data center which Google uses for its own products. Not only this, Google is committed to deliver the high performance SLAs to all its customers, which guarantees 99% of uptime from the infrastructure standpoint. By saying this, I would like to take a halt here and leave you all for the rest of the session with my team member, Yogesh, to walk you through the entire webinar. Wish you all the very best for the rest and enjoy your session. Over to Yogesh.
Thanks, Chirag. So good morning, everyone, and welcome to our webinar on containerization on Google Cloud Platform. My name is Yogesh, and I work as a solution architect in Sela Technology Solutions. So in this webinar, we will look at high level what are containers. We'll see how to get started with Dockers, and most important of all, how we can set up a containerized production grade environment on Google Container Engine, which is going to be pretty much the main focus of this webinar. So I'm assuming that most of you guys are already familiar with the cloud platform, with the cloud technologies, but the specific one that we are going to use is Google Container Engine, which is managed container as a service offering from Google. We'll later get into the details of this. So let's see the agenda at a high level. So this is what our agenda looks like. Now I do want to point out that the 3 topics that we see in the agenda are all big and complex topics by themselves. And thus, in order to cover them in under an hour's time, I have tried to keep them at a high level to understand its basic purpose. So just try to understand them at conceptual level, and as and when we see the demo, as and when we do hands-on exercises, things will start making much more sense. So let's begin. Now let's have a quick look at how the virtualization techniques have evolved over the time. In the very beginning, there was pre-virtualization world. I'm sure I don't have to talk much about this. Everyone is familiar with this. We all know that pretty much nobody uses this right now. But then the way it looked is everything physical. You have all the applications on the physical servers. In the physical data centers, no virtualization at all, so no sharing, no cost optimization, and it had its own issues, ton of issues. Then over the time came the concept of hypervisor-based virtualization, which are the VMs, which pretty much everyone is using nowadays. And then came the world of containerization-based virtualization, which was, I would call it that the virtualization was revolutionized by the world of containers. So now let's quickly see how VMs and containers work and what are the key differences between them. So in hypervisor-based virtualizations or VMs, the concept works something like this. We have a physical server which has a host operating system on top of it. And the key aspect of running this technology is the hypervisor, which does nothing but it emulates the underlying hardware. It emulates the entire computer hardware. And this is why each and every VMs that you run now on top of this hypervisor, all of them need to have a guest operating system. It creates a lot of issues. I mean, of course, it has a lot of advantages over over the pre-virtualized world, which were like using the physical machines, for example, cost benefit, easy to scale, and things like that. But then it also has its own set of issues. One, for each and every VM that you want to run, you have to duplicate the kernel resources. Each and every VM needs to have its own guest operating system, which not only consumes space but also adds added overhead on CPUs and memories, because now every operation that you're doing on this VM is going through the process of this guest operating system and the hypervisor, and also the host and the physical machine. So one, you have kernel resource duplication, and second, in cases like these, application portability is not really guaranteed. There are too many constraints, which a hypervisor provider you're using, what type of machine you're using, and things like that. So there's a very famous situation known as developers saying it's working in my machine, but then it's not working on QA or it's not working on production. So in cases like these, you don't have 100% application portability. Now let's look at how the containerization based virtualization comes into picture. How does it work and how does it help you? So now if you look, you have a physical infrastructure, you have a host operating system, but then on top of that, you don't have the hypervisor, you don't have guest OSs for each and individual containers, which are now mapping for the VMs over here. So the way it works is that the container engine, it not just emulates the hardware, but it takes the virtualization at the OS level. So to give you a simple description or simple explanation about it, consider containers as processes and not the system, which VMs are. So to give you an analogy, if you consider VM, consider them as booting up or starting a smartphone application, the smartphone, the entire smartphone. It has its own time, takes its own time. It has to go through all the boot up processes. For containers, consider them as a simple smartphone application instead of the smartphone. So starting up a smartphone versus starting up an application, there's way more difference. So these makes containers cost efficient. Of course, they make they help in faster deployment. You don't need to have duplicate kernel resources. They are all sharing the underlying host operating system. They don't need individual guest OSs. And in terms of other benefits, they provide guaranteed portability. We'll get into that in upcoming slides. And one of the key aspects for which containers are very famous these days are helping in building microservices architecture very easily. This is something that we will also see in the demo of how you can achieve it. To do this, I mean, it's not that it cannot be done on VMs, but there are too many manual and complex operations involved to set this up as compared to what you would do in using containers. So looking them side by side, you see that if you consider virtual machines, physical processor is all the VMs share. Each VM needs to have its own virtual processor, its own operating system, their own system libraries, and its own user code, the application which is being deployed on it. On contrary, if you see containers, Every containers share a physical processor, a virtual processor, and an operating system. And all an individual container needs is the user code which is being deployed in the container and the system and application libraries. So you see that it takes a lot of overhead out as compared to virtual machines. You have the virtualization at the OS level as compared to hardware level in virtual machines. And this is how it makes things more easier as well as efficient. So this is just a high-level overview of the containers. What we are going to check next is something which is the most famous and widely used container technology implementation in the market right now. So this is what Docker is. It's a container technology implementation. Now the containers concept has been there since late 90s or early 2000s, but it was because of Docker that containers gained extreme popularity. It's changed the way you work with containers. Just to give a short description, Docker is basically an open source platform. It is developed using Go programming language, and it has been implemented using Docker image specification and libcontainer specification, basically, which acts as the backbone of this container concept. Now, Docker used to be a platform for managing only Linux containers. Now, when I say it has 100% application portability, is because in last year, I think last quarter, Microsoft announced support for Docker containers in Windows Server 2016. And if I'm not mistaken, I think Mac OS X is also now supporting running Docker containers natively on their platform. So this makes Docker build, ship, run, and run any application on any OS anywhere 100%. You can run them on your physical machines, virtual machines, or even on private or public cloud. You can run them on Windows, Linux, Mac natively. Before this, if you had to run on Windows or Mac, you actually had to install a Linux VM and then run Docker containers on top of them. Let's see at a high level what the Docker architecture looks like. So if you look at this, considering the core components, you have a Docker daemon, which basically controls everything and does all the work for you when it comes to managing the containers. And then you have a client, which is nothing but a CLI, which is used to interact with this Docker daemon. So Docker daemon is just a runtime, a Docker engine running inside the host machine. This is what you can consider it. And then, like, if you get into the workflow components, you can pretty much easily map it to what you would do in VMs. So just like VMs have images, you also have Docker images, which are not exactly same as VM images, as they involve the guest operating system. The Docker images have been built using their own standards, using their own platforms. We'll also have a look at one of the ways of creating it. And then you also need something to store the image. So first of all, image, they are the specifications, and the containers, they are the implementations of the specification. You have registry wherein you store the images. You can map it similar to what you have Git repository or Git registries for your code base. So you have Docker has a public registry called as Docker Hub. You can easily find all the publicly used images, open source images over there. You can also host your private repositories, private registries. Google Cloud Platform has an option to do that, provides you this service. And then there's something also called as repositories, which is basically collection of one family of similar Docker images with different tags and different versions. So for example, you can have an Ubuntu repository wherein you have various Ubuntu images of different versions using different tags. So these are the workflow components that we spoke about. Now, before we get into the image structure, I want to quickly show you a small demo, just to get a feel of it, that how the containers are and how they look like. So what we will do is, let us quickly launch a simple container which is built on top of Ubuntu. We are going to install Tomcat and Jerry on it, and then we'll see how much time it takes, including the boot up time, and then you can pretty much relate it to how fast it is as compared to what you would do on VMs. So what I'm doing over here is that I'm trying to execute, so I'm instructing Docker to run this particular image. This image would be fetched from the Docker hub, which is a public repository. It will look something like this, just to show you how it looks like, just so that you get a feel of it. So these are the official repositories. You see that you have a Redis repository over there, Ubuntu repository over there. So similarly, what we're doing is that we are fetching a Tomcat 7 JRE 8 image from this public repository. Now, if you see, when I do it for the first time, it tries to search it in my local environment. And if it is not there, it tries to pull that image from the Docker hub. Now look over here that you are seeing that it is downloading in various parts. You see some hash code over here. We'll get into it of what exactly these things are to understand the concept of image and how they're built. And that's it. This is how much time it took to install the Ubuntu image, to install JDK, to install Tomcat, to boot up, and to start the Tomcat. So now this is how it is. So let's say if I do Docker PS, you'll see that there is a container that is running. What I'll do is I'll stop this container. And now if you see, if I try to access this, this is not accessible. And now when I try to start the container the second time, it knows that it is already there. It will not fetch it again. Plus, if I make any changes in the images, it will not download the entire image, but it will only download the relevant change. And this is because of the way the images have been designed. We'll now get into the way images, the concept of the images, how they are built and how they work. So now once I've started it again, I see the Tomcat application again. So getting back to the presentation, the Docker images are built on the layer structure. What do I mean by that? So this one of the way of creating a Docker image is to write a Docker file. There are a set of instructions, there are a set of templates, how you build this. So for example, if we consider the current Tomcat image that we have, a part of the configuration looks like this. So in the Docker file, I've given the instruction to use the Ubuntu latest as the base image, which is this one. Then I've gave the instruction, so the run acts as the keyword over there, and I want it to run the apt-get update. I'm installing JRE 7, I'm installing Tomcat 7, and at the end I'm asking it to start the Tomcat process. So now the way it maps to the Docker image layered format is that each and every individual instruction gets added as a layer. So on the base, you have the kernel, which is this. Then you have a base image, which is our Ubuntu image. And then on top of that, all your instructions get added as an individual image. And then when the container is up and running, any other manual changes that you do inside the container are written on this writable container. And you can save those changes and convert another image out of it. Now the advantage that it gives is that this shared layers or the shared images, they're not downloaded every time. So now if I change anything else in my Docker file, if I add a couple of more instructions, it is not always going to download the entire image because it knows what layers are changed and what layers are new. So it will reuse the existing layers and only download the delta. Plus, if I have some other containers which I also want to, which are also using some of the shared layers of it, they can be reused. This is how it, the containers are easy, flexible, and make the deployment faster. So like the other points that I mentioned, when the container is deleted, the writable layer is also deleted, but the underlying layers remains unchanged. So the multiple containers can share an access to the same underlying image. We already saw the demo. So now that we know what are, at a high level, how the containers are, how they work, or what they look like, is that sufficient? Now I can spin up as many containers as I want on my Docker host. provided that the resources that I am going to specify for the containers are available on the host. Right now, I haven't specified any resources, which by default means it can expand till the resources, meaning the virtual CPUs or the RAM that our Docker host has. But there are also ways in wherein I can specify that, okay, this container which is launching is supposed to have only 1 core and 2 GB RAM. So I can spin up as many containers as I want on a Docker host, given that the total resources consumed by the containers is equal to the Docker host resources. But then if you think of now a production grade environment, this is not sufficient. There are a lot of things that we need to take care of. If I start doing everything on a single host, it becomes my single point of failure. So I need a clustered environment. I need to think of failover. I need to think of high availability. I need to think of load balancing. There are a lot of other things. So now let's say if I have a clustered environment, imagine how complex it would be that I want to create a cluster of a certain container, let's say a front end of my application. I want to deploy it as a container, as a microservice, and I want to deploy it in 3 clusters. I have to go into each and every cluster, do the same operations again. If I want to control scaling of that, I need to mention which container is that I'm scaling. So all of those hassles, if I try to drill it down into the things that I'm expecting, is this. So I need much more things from containers. I need to somehow want to schedule the containers. I want a way to specify where my containers should run, an easy way to specify. If I have a 10 servers cluster, it should be easier for me to instruct somebody to do that. I want, if the containers are running, that's not enough. I want something to constantly monitor the lifecycle and health of my containers. If my containers go down, they should automatically spin up new containers. I want something to take care of it. I want scaling to be easier. If I know that, okay, now there is going to be a spiky traffic for a certain period of time, I want to scale up the containers, and after that is done, I want an easier way to scale down the containers. I want to do load balancing. If I want to specify this is the set of containers that I am scaling up, I want something which makes naming and discovery for my containers easier. Apart from that, I also need logging, monitoring, identity, authorization, debugging, introspection, and so on. So this is a huge list. If I start doing this manually, it's going to be one big headache, and then it's not really differentiating it from how the VMs are working now, apart from the fact that it is making deployment faster and things like that. So now let's consider this production simple general enterprise architecture into the production environment. So basically it's a web application which has a PHP front end and a Redis backend. Over here we have mentioned MySQL, but for now, for the example purpose, we are going to use the Redis image. So what it has is it has a front end, clustered front end of multiple servers, and one primary database and 2 secondary databases. So it basically takes care of the failover. It's highly available environment. There are load balancing options configured accordingly. I need to configure something which will do the health check, fixing of the crashed servers and things like that. So now let's try to consider that we have to build a similar environment on the concept of containers. So basically containers need management. If you use them independently, they're way more complex to handle. So for all of these things, I always said that I needed somebody to take care of this for me. So that someone is Kubernetes. Kubernetes is basically a container clustering solution. It takes care of all of these issues, and it provides a way of servicing all of these to you directly, launching containers on various clusters and tackling all of these things. The way it does is that the master, this is basically the high level architecture again. So you have a Kubernetes master, which is the key component of Kubernetes. It is the one that is doing all of these things for you: scheduling, health check, spinning up the crashed containers again, allowing you to just instruct to scale up and scale down, and taking all the hassles on itself, load balancing, discovery, all the things is something that Kubernetes does. So the master takes care of it. What you see over here, the minions are basically your nodes, your hosts, the clustered hosts. So each minion has a Docker daemon running inside, And then inside those hosts, there are containers which you can run. We will get into what pods are, what you see over here, but then consider this as client and consider this as the master. So the master communicates with the daemons, and whatever you instruct to the master using CLI, the master will handle it and then execute all of those things on those containers in its own way. Let's quickly look at the primary concepts. So we mentioned about nodes, which are the hosts. You have containers, which is basically a packaged a packaged libraries, a packaged set of libraries and user code, like we saw before. You have pod. Pod is basically a group of tightly coupled containers. It is just as a concept. We'll get, when we see the demo, things will get more clear and you will understand what pods are meant for and how they work. Then you have something called as labels. Now, when I mentioned that we need something for naming and discovery, so labels acts as the naming part. You can basically add key value pairs to the pods or to the group of your containers. You can mention that, okay, this is my pre-production front-end pod. This is my production back-end pod. This is my development test front-end pod, and things like that. And then there is selector, which is a way by which you can instruct the master that, okay, only scale my front-end pod which is in production. So then you will, to the selectors, you will pass that, okay, scale the pods which have label environment as the production and the pod as front-end. This is how it knows that which set of pods I want to scale up and scale down. Replication controller inside the master is the key component which takes care of all of this for you. And then services are the one which acts as the common entry point for your set of pods. They act as the load balancing medium, and they are the ones which help you build your application instead of in a monolithic way, in a microservices kind of way. So to easily understand all these components, I know that this is too much of a theory. So to easily understand, let's quickly take a 50,000 feet view of how whatever I said would work. So the user can basically interact with the master using API, CLI, or the user interface. So if I look at a high level, what I want is, I just want to instruct that this is what I need, and the master should take care of it and give me the result accordingly. So taking an example of the architecture that we saw, I just want to instruct the master that, okay, this is how my front-end container configuration is. This is the image specification. This is the configuration, 1 CPU, 2 GB RAM. This is the image which you have to fetch and install. And these are the additional configurations. So, and I want 3 clusters of it or 3 replicas of it. I don't want to take care of the headache of doing all of this installation. I just want to instruct the master, and I want master to do it for me. So the way it works is that I give the instructions, which is basically a configuration file. We'll see it in the demo. So the configuration files provides all of these specifications, what the container specification is, which is the image, how much configuration, what amount of memory, what amount of RAM. I'll give certain labels so that I can use it for scaling up and down. I can use it as labels and by using selectors. So I just give the instruction to the master. Now it is the master which decides, okay, these are the set of nodes that I have. Out of the nodes, this much memory or resources are free. So it takes care of deciding where it should be installed and efficiently using the underlying resources. It just passes on those instructions to the kubelet, which is the agent on each and every node. The kubelet then takes care of parsing the instructions and performing all the operations. So pulling the image from the registry, installing the image, configuring all the containers, spinning up the containers, sending the status back, and then the user fetches just the status. And at the end, your application, whatever instruction you gave is installed on, let's say, these 2 nodes, if you gave 2 replicas of it. This is how simple Kubernetes makes it for you, the deployment process. You just give the configuration, and all the other headaches, Kubernetes will take care of it for you. I'll quickly just move away from this theoretical stuff. Let's go through it quickly so that we can actually go to the demo and see things hands-on. So as I said, pods are group of containers, tightly coupled group of containers. So those containers, pods help them in sharing the namespaces, the volumes, the network namespaces, and giving a set of labels. Labels, as I said, are just key value pairs. You can mention the application is my application, the track is stable, or the track is canary, or let's say the environment is production, or the environment is pre-pod. The tier is front end, tier is back end. You can basically give any string name value pairs as labels. And then when you're using selectors, you can use the same labels as conditions in the configuration file. And then you can decide what set of pods or containers you want this operation to work on. So for example, in this case, if you give the condition app is equal to my app, all the 4 pods are basically matching those conditions. So whatever operation you are instructing is acted upon all 4 pods. If you say app is equal to my app and tier is equal to front end, then only these pods will have those configurations applied and things like that. Apart from this, there are other things that we will see how it is. Kubernetes, as I mentioned, helps you in reconciliation. It makes sure that if you have instructed, I need 2 replicas of this pod, so at any given point of time, it will have 2 replicas, even if the pods crashes. It will spin up new pods, take care of it automatically for you. It's very easy to scale the pods, we'll see in the demo. And then it also provides a way to do ruling updates, which is basically a way to achieve near zero downtime deployment. So if you have a cluster of pods, if you want to upgrade to a new version, it will start it pod by pod so that you don't have your entire environment going down. A quick overview on Google Container Engine. I mentioned that it is a container as a service. These Kubernetes can also pretty much run on standalone systems, on VMs, or also on cloud. So I did mention that all of that is easy, but then there are a few complex tasks like setting up the master, which is a tedious task. Now in Google Container Engine, since this is a container as a service, the Docker and the Kubernetes masters are already pre-configured and set up. You can directly start using them. There are other advantages also of this, crucial advantages that we will see at the end of demo. But then for now, just assume that this is container as a service offering from Google Cloud. And all the demo that we are now going to do is we would be doing on the Google Container Engine. So let's quickly start with the demo. We are going to deploy a web application with Redis and PHP. This is the kind of an architecture that we saw. And now if we map it to the concepts that we saw, this is what the environment will look like. So basically we need 3 instances of our front end. So we are going to have these 3 labels are the 3 front end pods, 3 replicas of it, which are going to be deployed on 3 separate nodes. You are going to have a front end service which acts as an entry point to these pods. It automatically takes care of out of these set of pods, which are the pods relevant to me. We'll also see how easy it is to set that up. Then we have a master Redis database pod with a service, and then we have 2 instances of slave database pod with its own service. And then we have a Kubernetes master, which in case of Google Container Engine is already pre-configured. So let's quickly start with the demo. Let me also quickly show you how the Cloud Console looks like. So this is basically the Google Cloud Console. We are going to use the Container Engine, which is Container as a Service platform from Google. So now if we see this diagram, what we need first is we first need 3 nodes. So let's see how simple it is to set this environment within minutes, which in case of VMs would have taken hours to do that. So the very first thing, like I mentioned, is we need 3 physical nodes. We are going to use the CLI interface of Google Cloud. I'm just selecting a default project to work with. Everything in all the cloud service providers work in different regions and zones. So the nearest one for us would be Asia. So let's just use that. And now, in order to spin up 3 nodes, all I need to do is just say this. Let me just clear the screen and start it. So what I'm doing is I'm instructing Google Cloud to create a cluster called guestbook having 3 nodes. I can also give configuration, the default configuration being 1 CPU and 4 GB of RAM. So it will, with this command, it will deploy or it will create 3 VMs with 1 CPU and around 4 GB of RAM. Linux image again. So if I look at this, the containers are being created in the background. We'll just quickly have a look at till the time it creates the container. Okay, so now if you look at over here, you will see that it is creating guestbook with total of 3 cores, 1 vCPU per node. The total memory size is around about 12 GB and the cluster size is 3. If you look at compute engine, which is the infrastructure as a service offering from Google, wherein you control individual VMs, you'll see that we have now 3 virtual machines for the guestbook of 1 vCPU and 4 GB RAM. Now the next step is to start, again going back to the diagram, we have the 3 nodes. Now let's start with, for example, let's say we start with the Redis database. Still doing it. Meanwhile, what I'll do is I'll show you the configuration files that we were talking about all along so far, so that you understand how simple it is to instruct the things that we are doing. So this is a YAML file. This is the template that you use for creating the deployment instructions. So basically, I'll just cover the basic things. So what we are doing is that we are going into kind is basically mentions what type of instruction it is. So when it means deployment, it means that you are creating a pod with a set of containers. Other options in kind is service, wherein you're mentioning that you're creating a service. So for this one, this is a pod. We are giving just a name to it, a Redis master. We are mentioning that we only need 1 replica of it. We are giving it certain labels, that application is Redis, role is master, tier is backend. And this is the container specification. So what I'm instructing is that this is the image. This is the Redis master image, which is going to pull from a public repository. And I'm mentioning that this is supposed to use this much CPU and this much memory and a container port for it. So with this, just with this set of instructions, okay, all I need to do is I need to instruct this Kubernetes command. So what I'm asking it to do is I'm asking it to create a deployment by referring to this file. I may have to go to guestbook and then launch this. Let's just give you a minute. These are the things about demo. They just stop working at the right moment. So okay. So now if I do kube control get pods, it will just show me that this is the container which is starting. So it is doing all the operations, starting the container. Meanwhile, I'll just show you how the service configuration looks like. So all that I do is I mentioned that this is the kind service. I'm asking it to install a service with this master, with this name. These are the label. And remember the selectors when I spoke about that, how will I instruct that this service is supposed to be for these replicas of pod? So the way it works is that I give it a selector and I give a set of key value pairs. So what it will do is that it will create a service with a load balancer and start load balancing to all the pods on these target ports, which are mapping with these key value pair labels. So if I check my Redis master pod, the labels are app equal to Redis role master and TRS backend. Over here, similarly, you will see that these are the same key value pairs which we have used it in the selector part. So now our service is up and running. What we will do now is that we will create the service. And if I do the services, you will see that this is an existing service which is for the Kubernetes master, but this is our service which we created. Now, just for now, note that it is only having an internal IP, not an external IP. We'll get into it later. So from the diagram, what we have achieved is that we have created the master pod for the database. We have created the Redis master, and we have created the Redis service. So similarly, I'll just quickly go ahead and create the slave pods and the slave service, and at the end, we'll also look at the front-end pod. So for now, I'll just quickly finish up creating the slave. We have the same problem here. So we have created the slave pod, and I'll quickly create the save service. So now if I do get pods, I basically have one instance of Redis master. In case of slave, we've given the exact same configuration instead of image being the slave image, and I've mentioned 2 replicas, so it has created 2 set of pods. If I do get services, you will see that there are so you have Redis master service and the Redis slave service. Similarly, I'll quickly create the front-end deployment. And we have the front end. So if I do get pods, I've mentioned for the front end 3 replicas, so it is creating now 3 containers. Meanwhile that it is creating that, I'll just show you once for the front end as well. So again, we have mentioned deployment as the kind. We have given it a set of labels. We have given it the specification, the image that it wants to fetch. This has the image as well as the PHP application that is in it, and these are the configurations. And at the end, over here you have mentioned that it is 3 replicas. Now the beauty of this is that it is doing this, it is it uses as different nodes as much as possible, so that even if your one node goes down, your application is still responding from the other physical nodes or from the other VMs. And in the end, I am just going to create the service for the front end. And now I have the front end service. The reason that I'm reconfiguring it again is that, remember when I showed you that all of these services, they don't have an external ID. Now the front end is what I want to be exposed to the outside world. So the way I do it is that along with giving the kind service, I'm mentioning that the type of the service is a load balancer. So what it does is that when I create the front end service, and if I check the existing services now, only for this front end service, it is assigning an external IP. So only this one is exposed to the outside world. So now if you look at this, we managed to create the single Redis master pod, 2 slave pods, 3 front-end pods, and the 3 individual services wherein only front-end service has the external IP which is exposed to the outside world. So just wait for creating, for it to assign an external IP to it, and then we will see the application that we have deployed within minutes in this production grade environment. So this is the external IP. Voila, this is our guest put application. So now imagine if you would have to do this installation, this kind of installation, even if you have the images on VMs, using VMs. This is basically the microservice kind of an architecture that it helped you create in such a quick amount of time. Now, the scaling part which I was mentioning is that now imagine that all of a sudden you think that your 3 instances of your front end are not enough, and you basically want to have 2 more instances of the front end so that it has enough resources and power to serve the kind of traffic that you're getting. All you need to do is that mention scale the deployment, which is with the name front end, and change the replicas instead of 3 to 5. And that's it. If you do the pods, you will see that it has now created 2 more front-end instances. And once you know that you're done with the peak traffic, you can scale them back to 3, and it will start removing 2 extra pods. This is how fast and efficient it is. So in the end, I'll just mention the advantages of using GKE that I was talking about. We saw that how easy it is to scale the pods, but then like I mentioned, you can scale only up to a level till the time you have the physical resources, meaning 3 cores and around 12 GB RAM of configuration that we had in our cluster. Now Google Container Engine, apart from providing you managed master, also gives you an option to scale the underlying VMs, so that you can not only scale the containers, but also can scale the underlying hosts so that you can spin up more containers if that is the case. So because of the time restriction, I'll have to quickly end this. I hope the demo and the information that we could manage to give you in an hour regarding 3 big topics was good, and I hope that it helped you. So I want to thank you all for attending this webinar. We will start taking questions now. You have an option of putting the questions in the chat. You can put the questions there, and we will start answering those questions accordingly. I think we have a question. Let me just see them. Okay, so okay, so I see that we have a question from Nitish. He's asking that can we say that it is kind of similar to Solaris zones? Uh, I think it is. I'm not really entirely sure of what differences there are, but then you can, I mean, if you're asking about Kubernetes or basically Google Container Engine, there are various other platforms which provide the same services. For example, even Amazon has something called as ECS, which is Elastic Container Service, something similar to the Google Container Engine of which is provided by Google Cloud. I'm just checking if you have some other questions.
Yes, please.
Okay. Right. So how is this service different from Amazon framework? Like I mentioned, technically it is the same. Kubernetes, as I said, can work on public cloud, private clouds, virtualized environments, or even physical machines. Google provides it as Google Container Engine. Amazon provides it as ECS. I would say that there are differences in terms of business-wise. For example, eventually you're using the cloud resources underlying. So Google Cloud Platform comparatively is way more cheaper as compared to Amazon Web Services or Azure. Even Azure, I think, has a similar container platform on it. The other thing is that Kubernetes is built from Borg, which is an internal 10-year-old container management system, proprietary container management system of Google. So Google is the one who created Kubernetes and made it open source. So even in that way, if you consider Google's product, basically it will work much more efficiently on Google Container Engine, considering both have been created by Google and is also supported on that. Yes. So there is another question that I see that I have heard Swarm is the alternative of Kubernetes. Swarm, yes, is alternative of Kubernetes, but as per my personal experiences, Kubernetes is much more evolved. It's been handled by a bigger, open source public group. So there are too many improvements and advancements which are coming in Kubernetes continuously. The other thing that I mentioned is, as I said, Kubernetes was evolved from Google's product, which is Borg. There are already way more better things which Google has added in it from their experiences, past experiences or failures in the Borg project. So I would recommend Kubernetes, and I can see that it is way better than Docker Swarm, which is only coming from the Docker part. The other question that we have is, when we talk about clusterization, how does it manage to switch or fail over? If you can, okay. So like I said, master over here does that thing for you. If I go a couple of slides back, you saw that when we created a service, we gave it a way to identify which all pods it is supposed to connect to. So always your entry point is going to be the service. So now imagine in the front end, even if one pod goes down, the replication controller keeps monitoring all the pods, and if it crashes, it automatically launches a new pod depending upon what your configuration is. Meaning, if you have mentioned that you need 3 replicas, replication controller makes sure that any given point of time, your configuration will have 3 replicas. If one of your pod crashes, it will automatically launch a new pod. So this is at the container level. Now, if you're talking about failover or switch at the physical node level, this is handled by the cloud platform. So let's say one of the node goes down, you still have 2 nodes there, and internally making sure that it is redirected to the service, the cloud platform manages it. Over there as well, you have an option to do health check, monitoring, spinning up new nodes, and all of this can be done also on Google Cloud. So this is how it handles the replication, the failover, the high availability. How would you recommend this to major banks for adoption? Will it be the selling point? Could you please elaborate? Are you talking about Google Cloud be the selling point or containers be the selling point? I think this question is from Manish. If you're talking about containers, I mean, they're not really, dependent on uh, any specific domain. One of the things which just I want to quickly explain, which is not a part of this underlying webinar, is that people say a lot that Docker containers are not secured. Okay, I mean containers are less secured as compared to virtual machines. I would say that they have they have much more security aspects. Considering that in case of VMs, you just have all the VMs are totally isolated, so the security aspect is easier. And considering that you're sharing a lot of things in container, the security aspect being difficult, that doesn't mean that you cannot make containers secure. You can still make containers secure. There are still a lot of existing ways of doing it, simple configurations that you can do. It is just that you have to take care of security in a bit different way when it comes to containers. But then the advantages that it gives you over VM are way higher. And just because there are too much effort involved in making things more secure when it comes to container, you cannot just ignore how much efforts it is saving you for managing the entire infrastructure when it comes to production environment. So yes, we do recommend Google containers to all the domains, not just banking specifically. Any other questions? Okay, so I guess that's all for now. So again, I want to thank you everyone for attending this webinar. You see our contact details on the screen. If you think if we can assist you in any way for helping you migrate from your virtualized environments to the container services, if we can help you in building CI/CD pipelines, which containers is most efficient for, if you think that you need help to move from a standalone environment or from a virtualized private environment to cloud services, we can help you in all of this. You can contact us on all the given options below. You can contact us on the email or the phone, or you can visit our website to get more details about it. So thank you everyone again, and have a good day.